Today I'm going to be doing a reaction video to the series Secrets of the Quantum. You can watch this on Plex for free, so I suggest if you're interested in the topic that you watch the entire thing. So what I would like to address in this video is specifically the question about whether light is a wave or a particle. So prior to the section I'm going to be showing here, it's explained that light for the most part appears to be a wave. But now he's going to try and convince us that light is, in fact, a particle.
It's far from perfect, but hopefully it'll give you a sense of the physics to help you understand why thinking of light as a stream of particles solves the mystery of the photoelectric effect. In this analogy, these red balls represent Einstein's light quanta. And those cans over there are the electricity held in the metal. Now, in the original experiment, they made electricity flow from the surface of the metal by shining light on it. In my analogy, I'm going to try and knock those tin cans over using these red balls.
So he's trying to show that no matter how much red light you shine,
no effect.
It has no effect.
That's just like red light. According to Einstein, each particle of red light carries very little energy because red light has a low frequency. So even a very bright red light with many red light particles can't dislodge any electrons from the metal plate, just like the red balls. Now I'm going to use heavier balls, like these blue golf balls, and I'm going to try and knock off the tin cans with these. They're like the ultraviolet light in the experiment. Now, each individual light particle carries more energy because ultraviolet light is higher frequency. Just a few of them, like a dim ultraviolet light, are enough to knock the electrons out of the metal plate and collapse the gold leaf.
Okay, so that's his demonstration of why we should think light has to come in these particles, because each particle contains a variable amount of energy. And they say, classically, it can't be explained why you turn up the red light up to its brightest intensity that that you'd think that would deliver more energy to the target, but it doesn't. Just like the light, ping pong balls he was throwing at the cans, there's just not enough energy in each of those ping pong balls to knock over the cans. So we are left with this strange quantum thing where like light acts like a wave in every which way except for this way. So we are forced to accept that light is a particle. And so that's kind of a conundrum, right? So is there a way to think about this? Is there a solution to this problem so that we can get back to our more common sense idea that light is just a wave? Okay, so I'm going to react to this video by suggesting that there are other ways that this problem could be solved other than saying that light is actually a particle, like a stone that you throw. Okay, so I'm going to suggest it this way. So he showed throwing like the red balls at these cans and then not being able to knock them over. Okay. Now, what I'm going to suggest is that light still comes in waves, but that they come in, say, a wave packet. And so they're like the balls in the sense that they have a finite length to them. The packet could be, say, as short as a single wavelength, which could be represented as a simple sine wave, up and down. Just a single one of those. It could be. Now, in order to explain why is it that the red light uh, can't knock over the cans, but yet the blue light can, I'm going to say we only have to make one assumption, and that is that for all light, the amplitude. So the amplitude is the distance between the top and the bottom of this wave here. That's the amplitude. That the amplitude is identical for all light waves. Okay. Now, if that's true, then what happens is that the amount of energy that this light wave impinges upon a target will depend on like how many of these things hit the target per unit time rather than amplitude. Because what's confusing the scientists is that they think that light, when you turn up the amplitude, changes the amplitude of the wave. So we turn the red light up to like this, and then you think, yeah, that's got to have the energy, but no, that's not what happens. What happens is that no matter what your light bulb is doing over here, uh, all of the light waves of all frequencies are coming at exactly the same amplitude. And the reason why the blue ones can knock the can and the red ones cannot is because the blue ones have a higher frequency, which means that you can stuff more of them. You can stuff more of them in per unit time. So you can stuff like four in the space that you could have stuffed one in. Okay, so this amount of energy is enough to knock the cans. So getting back to his analogy of the cans at the arcade, it's like you take the red balls and you throw them, and yeah, they can't knock over the cans. But let's say we load those same balls into like super machine gun Nerf gun thing, and so we can deliver like 10 times as many balls at those cans per second than he could just kind of throwing them onesies or twosies at a time. And if you did that, then you could see that the cans don't have enough time to react. They absorb the energy of the previous ball to the point where, yeah, the Nerf machine gun could knock over those balls with even foam balls. So that is one alternative. Now you might wonder, taking this one step further, is why is it all waves would have constant amplitude? And one of the evidences of that is actually the formula for the energy of a light wave, which is the energy equals H, which is Planck's constant, times F frequency. Okay, and that's it. They say red light has much high. I mean, red light has much lower energy than blue light. I mean, that would seem kind of obvious that this is frequency in cycles per second. So any bigger number here is going to produce a bigger number there. But the important thing is that we have H here, which is constant, right? This is constant, Planck's constant. And actually what Planck's constant is it represents the amount of energy in any single wave of a light thing, right? So because this is constant, this shows that the amplitude, in order for this formula to work, the amplitude of every single light wave has to be constant. Another interesting thing here is that this is often said like the energy of a single wave of light, but actually this is cycles per second. So this is actually the amount of energy impacting on an object from a full second worth of light waves, is what that is. So you can see that the blues having higher frequency will of course have the higher energy, right? Just because there's more of them per unit time. So that will finish my comments. If I don't know if this has been considered by other scientists, it seemed to be a fairly obvious other alternate solution without resorting to making electrons, yeah, making light as a particle.